Hello. All right. So today I want to share with you one particular project that I got involved in the Smith Group for the last few years, in which I designed, synthesized, and developed a series of silicon reagents that we call them siloxane transfer agent, and these reagents used in the cross-coupling reaction. So for those of you who are not familiar with the cross-coupling reaction, catalyzed by palladium, this is probably one of the most important transformations in organic chemistry for the construction of natural products, diverse functional group, functional material, and biological active agents. So in this particular reaction, the metal palladium has a very special power. It can bring together two organic molecules and form the carbon-carbon bond between them. There are two coupling partners in this reaction. The nucleophilic coupling partners usually an organometallic species in which the metal usually boron, zinc, tin, or silicon, and the electrophilic coupling partner usually an organic halide, sometimes a triplet or mesylate. Some of you may remember that the Nobel Prize in Chemistry 2010 was given to Professor H, Suzuki, and Negishi for their discovery and development of this palladium catalyzed cross-coupling reaction. And in fact, this reaction has been applied in multiple occasions in industrial process, making diverse functional material and biological active agents. So even though the reaction has been well studied and developed for the last 50 years, as far as green chemistry is concerned, there's still significant limitation. I just list some of the challenges over here, and the first thing I list is this reaction still requires stoichiometric amount of toxic heavy metal like zinc or tin in the reaction. And besides two coupling partners, they usually require an additive, so like fluoride or strong base, to activate the cross-coupling. And this reaction usually requires high temperature and extended reaction times. Also very important is that this cross-coupling reaction usually, in order to make the two coupling partners, require multiple synthetic manipulation, and sometimes very difficult to just isolate and purify these coupling partners. I tell you before that the typically employed organometallic species in the cross-coupling reaction is organoboron, zinc, tin, or silicon, but the focus of my talk today is on organolithium reagents. So these are probably one of the most often used reagents in organic synthesis. They are very cheap, they can be commercially available or easily repaired in the lab. And also, these organometallic species over here usually oftenly repaired from the corresponding organolithium reagent using a transmetallation process. So we ask ourselves a question: if it is possible to use the organolithium reagent directly in the cross-coupling reaction, then that would be a very atom economical approach, because we can bypass the step of making this reaction right here, and we can avoid all the waste associated with these metals. So that's the focus of our research, is to try to figure a way to use directly this organolithium reagent in the cross-coupling. So the first person to try this concept is Murahashi in the 1980s, and he showed that it's possible using vinyl lithium to react with this vinyl iodide and little bit of palladium, about 5%. He found that there is indeed the formation of the cross-coupling product in 40% yield, and the reason for the low yield is because of something we call the homocoupling problem. This vinyl lithium is so reactive that it can react with this vinyl iodide without the palladium in a process we call lithium halogen exchange. The lithium and the iodide swap place to generate these reactive species in the solution, and this can react to generate the undesired byproducts in significant amount. So I tell you that Negishi earned the Nobel Prize in Chemistry 2010. And one of the reasons for that is because he's a very clever chemist, and he introduced into the same reaction zinc chloride, excess zinc chloride, to convert all the vinyl lithium into the vinyl zinc. And the vinyl zinc react efficiently with the vinyl iodide, generate the desired cross-coupling product in 95% yield with very minimal amount of the undesired byproduct. So if someone want to take this process, this reaction, and to make this cross-coupling product in industry. So on ton scale of the cross-coupling product, so maybe in the end you may produce a ton weight of zinc at the waste. So if you don't want to use zinc, right, you may use tin, so that also not a very sustainable process as well. So in the Smith group, what we use is we don't use zinc, we don't use tin, but we use an organosilicon reagent of this structure right here. We call this reagent siloxane transfer agent. And what this reagent does is that it captures the organolithium, and the resulting intermediate can be react with an electrophile in the presence of palladium catalyst and a little bit of copper to generate the cross-coupling product. So in this reaction, very important is the transfer agent is regenerated back after the reaction and can be used for another reaction. So if you look at this reaction right here, it's a very atom economical process in which the only ways in this reaction, if you can recover back the transfer agent, is the lithium salt. And the condition for the cross-coupling is mild enough that a wide range of functional group can be tolerated given a different cross-coupling product and good to excellent yield. And like I said, it's very important to find a transfer agent that can be easily recycled and reused after the cross-coupling. And we go into design and synthesize a series of analogs of these transfer agents, and we found that this structure right here can be recovered by flash chromatography. So by introducing brown test base into the structure, the siloxane transfer agents can be easily recovered by acid-base extraction after cross-coupling reaction. Nonetheless, the transfer agent in some cases proved to be less than optimal, and we asked ourselves, can we go one step further? If we can incorporate the transfer agent into a solid support, that would be very significantly simplify product purification, the siloxane recycling, and that could significantly facilitate the adoption of our chemistry but for the scientific community, that might advance our chemistry for other applications. So last year we showed that it is in fact possible to incorporate the transfer agent into a polymer support. I had a picture shown over here, and the way we make this polymer is from the very cheap commercially available material right here. In a few steps we can make this monomer which undergo a ring opening metathesis polymerization to make the desired polymer in near quantitative yield. And this polymer is soluble in organic solvent, ether, THF, acetone, but it is insoluble in water and acetone natural. So the way we run the reaction is we first dissolve the polymer in solvent, and then we introduce the organolithium, introduce the catalyst and the electrophile to generate the desired cross-coupling products. In the end, the reaction mixture will introduce with acetone natural, so the polymer precipitate out, and we can just filter, dry, and reuse them. So I show here that the polymer can be reused for at least 3 cycles, giving excellent to good yield of the desired cross-coupling product. So you may notice that even though the polymer can be recovered near quantitatively after each cycle, but the yield actually dropped about 10%. So we analyzed the recovered polymer, and it seems like there is an increase in the higher molecular weight species in the recovered polymer after each cycle. And we believe the reason for that is because of polymer cross-linking. If we have a polymer in solution, we add the organolithium, it attacks the siloxane, and the resulting alkoxide can attack another silicon on another siloxane unit or a different polymer chain, generate a cross-linked polymer right here. And the cross-linked polymer is not as effective as an original polymer, and that's the reason for the decrease in reaction yield after each cycle. So the recent trend in organic synthesis is emphasize on the harmonization between reaction efficiency and the environment. And so recent research has been focused on finding a good solid support that might be recycled indefinitely without no loss in reaction efficiencies. So this is our first generation polymer. So we take into all the consideration and come up with a second design for the second polymer that might be better. So I don't have enough time to go into detail, but in the end we decided to choose cross-linked polystyrene as the second support for our second generation polymer. So the way we make this from 2-bromobenzaldehyde, in a few steps we can make this monomer undergo suspension polymerization with styrene, using this tetrahydrofuran-based cross-linker to make the cross-link polystyrene, supporting the siloxane transfer agent with a picture over here. And by design, this polymer is insoluble in solvent but show good swelling property in solvent, cross-coupling solvent, which is THF in our case. So we run the cross-coupling reaction using the same standard reaction I showed you before, and it actually gives 96% yield of the desired cross-coupling product, and the polymer can just be easily filtered, dry, and reused. So after 6 cycles, it looks like the yield pretty much stay the same, and the polymer can be recovered near quantitative lift after each cycle. So is it possible to use different nucleophile and maybe different electrophile after different cross-coupling reaction using the same batch of polymer? And we show here that using the same batch of the second generation polymer, is it possible to run 10 different reactions using different nucleophile and different electrophile to generate the desired cross-coupling product and good yield? You may also notice that some of the functional groups like cyanide, ketone, are traditionally thought to be incompatible with organolithium reagent, can also be used in the cross-coupling reaction. And we also use aerobromide, also work as well. So far I show you that using our siloxane transfer agent tactic, we can able to form the carbon-carbon bond, but we also able to form the carbon-nitrogen bond using our tactic as well. In this particular example, phenolithium is added into this siloxane transfer agent, and then we add this hydroxyamine in the presence of a catalytic amount of copper to generate the desired aniline in 98% yield. Also in this reaction, the siloxane transfer agent is recovered back after the reaction and can be reused again for another reaction. So this belongs to a group of reactions called electrophilic amination, in which using an organometallic species, zinc, tin, boron, in some case silicon, titanium, or zirconium, react with an electrophilic source of amine, hydroxyamine or chloroamine, to generate the desired amination product. And this organometallic species again usually derived from the corresponding organolithium reagent. And our method is probably the first method to generally use organolithium reagent efficiently in the electrophilic amination to generate the amine product. So using this method, we show that you can get a wide range of amine, either acyclic amine or cyclic amine, 5, 6, 7 member rings. And we also try different organolithium reagent. It also work in decent yield. So we also try using our polymer in the amination. In this process, the phenolithium can react with the hydroxyamine mediated by this polymer, giving the desired amine in good yield, and we can recycle the polymer and reuse it after 3 cycles. So if you look at this reaction right here, the polymer can be purified by precipitation and then filtration. The amination product can be purified by acid-base wash. So in the end, this process is a chromatography-free purification process. So the way we envision we can go from here is to try to expand the substrate scope of the reaction. Not only use auriodine, aerobromide, but also use aurochloride. We might try using our siloxane tactic to make other type of bond like carbon-oxygen bond or carbon-sulfur bond. We also think about recycling the palladium, and the way we're thinking about doing that is maybe install into our polymer a phosphine ligand that can chelate to the palladium, so that not only we can recycle the transfer agent but also recycle the palladium as well. And we're also thinking about using flow chemistry. We're thinking about maybe coating the inside of the flow microreactor with the polymer so that we can run reaction in flow fashion. So in summary, in the Smith group, we develop methods for the direct use of organolithium reagent in making up carbon-carbon and carbon-nitrogen bonds. And this method take the advantage from the use of the organolithium reagent. This is again very commercially available or easily repaired. And this process has high atomic economy, in which you can go directly to the target without having to go through all the organometallic species, and in turn you can avoid all the toxic waste associated with these reagents. And you may also notice that our reaction use very mild reaction condition. Reaction will run at room temperature and usually done within a few hours. So all the chemistry was possible because of the use of a siloxane transfer agent developed and discovery and developed in the Smith group. And I also showed that we were able to incorporate the transfer agent into a polymer support, and this polymer is air stable, very easy to handle, and it significantly simplify workup and purification. Especially the second generation polymer seem to be very readily recyclable. So overall, we think that this chemistry right here really had the potential to provide greener and more sustainable chemical process. So we want to thank the funding agency, the NIS, to provide funding for our research. We want to thank the support from the University of Pennsylvania. I personally want to thank my boss, Professor Amos B, right here, who really recommended me to come here and give a talk, and all the members from the Smith group. So if you have any question, I would like to take it. Thank you.
Any questions for the speaker? Okay.
So this transfer reagent that you developed, is there any possibility to make it catalytic? How many mole percent you are using? One equivalent or?
So for the transfer agent right now, we're using stoichiometric amount of the transfer agent to capture all the organolism we're using in the reaction. If we had less transfer agent compared to the organolism, you see all the byproducts. So we need to use stoichiometric amount of the transfer agent. But the good thing is we can recover back all of them, maybe most of them after the reaction, and reuse them. So the idea of we're also thinking about the idea of using catalytic amount of the transfer agent, but maybe that can be applied into the flow chemistry system, that if we can use that in the flow, so that we can use a little bit of the transfer agent in the micro reactor, so that if we flow through the organolism slowly enough, that we don't need to use a lot of the transfer agent. So that I think that might be where we can develop a method for using the catalytic amount of the transfer agent.
Yeah, because once you do this reductive elimination, right? Or you can see when the R minus comes out from silica, you get
right.
O lithium that might clip back to give you the your transfer reagent in the system.
Mm-hmm.
That's how you can think of making it catalytic. Yeah, I don't see any other stuff. You know, once you are done, your transfer reagent is coming back as such, I guess.
Right, right.
It should be catalytic. I don't know.
Any more questions?
Thanks. With your transfer agent, you had just the single compound, like to start with, and then you moved on to making the polymeric form. My question is really based upon the efficiency of the process of the polymer versus having the original single. Obviously, there's a solvent cost, energy cost in preparing the monomer and then doing the polymerization reaction. So how many times would you have to have the polymer version recycle so that it would actually be greener, depending on what metrics you put to that, than essentially your model single compound?
So I believe so far the maximum amount, the time I tried the reaction is about maybe 10 or 15 times reaction, 10 different reactions using the same batch of polymer. We haven't tried going further than that, but I think that based on the result we got, it's possible to even run longer, many more times. We show that the polymer seems to be stable, and the efficiency pretty much stay almost the same after about 10 cycles. So I think that's we can compared to other monomeric transfer agent, the polymer is really the way to go, in which we can just use the same batch, and it's very easy to isolate and dry and reuse again.